A very good afternoon to all present. I would start with thanking the organizers for inviting me to this wonderful workshop and letting me speak here. So today I will speak about the conjugacy classes and normal complement problem in modular group algebras. So this is a brief plan of my today's talk. First of all, I will give some preliminaries, then I will discuss these two problems related to the study of unit groups of group algebras. In this conjugacy class problem, we discuss about this status of this problem over some finite p groups, first for the even prime and then for the odd prime. And then normal complement problem we discuss for some of these classes of groups. When we establish some results for conjugacy class problems over finite p groups, then we started working on this problem for modular group algebras over groups which are not exactly p groups. Suppose they are divisible by say 2 primes, their order is divisible by 2 primes. So surprisingly, we found out that the results obtained in that direction actually helped us to deduce a solution to this classical normal complement problem. So in my today's talk, I will just list some results in this problem that we have obtained, and will focus more on the connection between these two. So in the end, I would give some future questions which arise out of this part of my thesis. So let us start with the definition of a group ring. Suppose we have a group G and a ring R, then set of all formal linear combinations, this forms a ring under these usual operations of addition and multiplication. And if the ring in particular we take to be commutative ring, then it turns out to be an algebra over R. And moreover, if the ring has characteristic P and the group has order and the order of the group is divisible by P, in that case we call it to be a modular group algebra. Now let us see what the augmentation map is. If we map every element of Rg to the sum of its coefficients, then we call this map to be a augmentation map, and it's a group, it is a ring homomorphism. And kernel of this map is set of all the elements which are mapped to 0, and it forms in this set omega Rg forms an ideal of Rg, and we call it to be an augmentation ideal of Rg. And moreover, if we take all the invertible elements of Rg who map to 1 under this augmentation map, then we call those units as normalized units, and these units actually form a subgroup of the unit group, which is called the normalized unit group of URG. So corresponding to any subgroup of G, we can actually construct an ideal in Rg. So in particular, if we take a normal subgroup, then the ideal generated by these elements h minus 1 in Rg is actually a two-sided ideal, and it is denoted by this gamma h. And also, if we consider this to be a transversal of H in G, in that case this set actually turns out to be the basis of this two-sided ideal as an R module. Now this canonical involution of G, which takes every element to its inverse, actually plays a very important role in the study of this group algebras, and it can be extended to R module homomorphism also in the obvious way, takes each element to this. All the elements of Rg which remain fixed under this map are called the symmetric elements of Rg, but the elements which satisfy this x star equal to minus x, they are called the skew symmetric elements. And all the normalized units which satisfy this equality, that is V star V equal to identity, they also form a subgroup of VRG, which is called the unitary subgroup, and these elements are called the unitary units. So these were some of the definitions, and now we have this standard result which we will be going to use throughout further discussions. Suppose we take this canonical homomorphism, then we can extend it to an R algebra homomorphism in this natural way, then it gives rise to a R algebra isomorphism with gamma h as the kernel. And also, if this gamma h is a nil ideal of the group ring Rg, in that case we have this group isomorphism also. So also, if the ring is commutative, then the unit group of Rg is nothing but the direct product of units of R and all the units of augmentation 1. One can easily see that any normalized unit can be written as 1 plus some element of augmentation 0, but if we take the ring to be a field of characteristic P and G is a finite P group, in that case the reverse inclusion also holds, because it's a nilpotent ideal in that case, so equality holds in this case. G is a finite P group. So this was all about some of the preliminaries. Now I will be discussing about the unit groups of modular group algebra, and this study is one of the fundamental things in the study of group algebras. So not much information about the structure of unit groups of group algebras is available, but actually in this paper Robert Sandling first of all gave the basis and invariants of the normalized unit group of VFPG, where G is any finite abelian P group actually. But if the group is non-abelian, in that case not much like information is available about the structure of the unit groups. So people started studying like these groups through their conjugacy classes. So in this paper it was Coleman who first gave some results on the conjugacy classes, and then after that people started studying what can the size of the classes in these classes of group algebras be. The first result in this direction was that there exists no conjugacy class in VFG, where G is a finite P group actually, which has size P. And then this was modified by authors in this paper, and the result says that actually square of the size of field is the lower bound for any like size of any non-trivial conjugacy class. Again putting some properties on the group G, there was some other result, but these are like for any finite P group. So now we can formulate what the conjugacy class problem is. It says that what P prime powers can actually occur as cardinality of conjugacy classes in modular group algebras of finite P groups. As we saw that this is the least divisor of the length of any conjugacy class, even though we don't know whether in VFG we can give a general element which actually has this class length of this size. So motivated by this, we started working on this problem, and we started with the smallest non-abelian P group, that is the groups of size 8, and for particularly these groups we have these as the class sums, and they form the center of this group algebra FH as an F module, and following these notations we obtained this first result. It was regarding the structure of this quotient group of VFH with its center, and it turns out to be elementary abelian 2 group with these generators. And based on this lemma, we were actually able to prove that in this case, that is for any non-abelian group of order 8, any non-central element of VFH has exactly class size same as the square of the size of field, which we just saw that it's the lower bound. Here it's actually attained, like it's equality here. Okay, so based on this result and one more, we were able to prove that to obtain the class length of elements of the groups H cross E, where E is a elementary abelian 2 group. So this was something about the class length. Now let us talk about the representatives of classes in these groups. So since a group of order 8 is actually extra special 2 group, so in this case it is known that the unitary subgroup is actually a normal subgroup of VFG. So in this case we obtain these elements as the class representatives corresponding to non-central elements of first for quaternion groups, then these are the elements which give complete partition of V star F D8. Okay, then this was these were some of the results that we obtained for 2 P equal to 2. Now for an odd prime P, we actually proved this result, which was corresponding to class length of group elements actually. So if we take any finite field of characteristic P, G is a finite P group, and P is an odd prime. In that case, for any non-central element of G, the class length of G in VFG is actually square of its class length in V star FG. And in order to prove this result, the symmetric and skew symmetric elements of Fg play a very important role. So, if S1 and S2 denote the set of these elements respectively, then omega Fg, since P is an odd prime, omega Fg turns out to be direct sum of these two sets. And since we have seen that Vfg is nothing but 1 plus omega Fg, so in order to find the centralizer of G, small g in G, in Vfg, we need to see only the elements of omega Fg which commute with G, and which again our work is like split into these two. We have to see both of these sets individually. So, suppose we take some element from here, skew symmetric element, so V star is minus V, so V turns out to be in this form, where G is the representative of coming from the partition of G by these pairs. Also, there is a 1:1 correspondence between the unitary units and the skew symmetric elements. So, this form gives us that size of V star and S2 is this. Now, making use of these two lemmas, we will actually able to prove the main result. And first lemma says that corresponding to any non-central element in VFG, corresponding to any unitary unit which commutes with this non-central element, we have an element which is skew symmetric and vice versa. So, also if in particular this element is a unitary unit, in that case this size of the centralizer of this element in VFG is nothing but the product of number of elements which are symmetric and commute with V and the number of skew symmetric elements which commute with V. So, making use of these two lemmas, we were actually able to prove that size of class of G in VFG is square of the size in V star Fg, and for that first we take some element which is skew symmetric and commutes with G, then we can break its support into two parts, where these elements of the support are coming from centralizer of G in G, and the rest of the part is from outside the centralizer of G in G. So, we can actually construct an automorphism from here, from G to G, which is defined like this, where this G is the particular this from which we started, and if we construct a group generated by this phi G and consider its action on G, then we can see that because of this equation, support of beta is actually closed under this action, and the coefficients on the orbits agree. And therefore, if we take any orbit of some element which is outside the centralizer and denoted by OH, then support of beta turns out to be the union of these orbits. And since P is odd prime, here any element, orbit of any element and orbit of its inverse are actually lie in different orbits. So, corresponding to this element with which we started, and it was skew symmetric, we can construct an element which is actually symmetric and commutes with G. So, we made a 1:1 correspondence between CS2G and CS1G, and hence the sizes are same. So, now making use of the lemmas that I gave just before this proof, we actually conclude this. So, based on this result, we were actually able to conclude some more results, like if we have some element such that its pth power is in center, then we can explicitly give its class size for any group, finite P group G, and then if the class of G is 3, then making use of this lemma, if we put further condition that commutator subgroup is elementary abelian, then for any element of G in G, we can say this is the class length. Now, this was the case for the conjugacy class problem, but only for finite P groups. Now, moving on to the next section of the talk, which is normal complement problem. First of all, I define what is it. Since all the group elements are always invertible in RG with augmentation 1, so a very natural question then is posed, which was, what are the groups G and rings R such that we can find a homomorphism from VRG which is split by the natural inclusion of G in VRG. Okay, if this happens, then we can write VRG as an extension of G by kernel of this map, say N. Okay, so this problem emerged as very significant area of research because of its connection with the isomorphism problem, and this connection is like established for integral as well as modular group rings. In case of modular, in modular case, it was Frank Roll who in this paper actually proved that normal complement problem is actually sufficient condition for the existence of this isomorphism problem to be true. So he proved that suppose we have some finite p groups G and H such that Fg and Fh are isomorphic, where F is the field with p elements, and one of G and H has a normal complement in VFG or VFH respectively, then we can say that G and H are actually isomorphic. So motivated by this, people started working on this normal complement problem, and there are several classes of groups for which this holds true, normal complement problem, and hence the isomorphism problem also holds true. The first counterexample in this direction was the dihedral group of order 16. It doesn't have a normal complement in F2D16. Now these are some other classes for which it holds, it doesn't hold. Now we started studying this problem for the groups which are not p groups. So to start, we started with dihedral groups whose order is divisible by 2 and p. So the first result in this direction that we obtained was for dihedral groups of order 6, it is S3, and over the field with 3 elements we actually proved that it has a normal complement. S3 has a normal complement, and we made use of this theorem actually, which is general. It says that if we have the field with 3 elements and A is an elementary abelian 3 group, then this group G, which is extension of C2 by this A, has a normal complement in VFG. And we actually made we split this, and using this map, it takes 1 plus gamma is element to raise to this power augmentation of these elements. So the kernel of this map actually turns out to be the normal complement of G in VFG. So this kernel we actually like calculated in this case, and it turns out to be this N. Now this was the case when F is the field with 3 elements, but if F has more than 3 elements, in that case we actually concluded that this doesn't hold anymore, it doesn't have a normal complement. But we made here we made use of conjugacy classes information to conclude the result. So for that, let us first of all assume this is the presentation of D2PM, and assume that A is the normal subgroup of D2PM. Then we have VF D2PM is actually extension of VF this C2 by this 1 plus gamma A, and here this is isomorphic to F star. So it is a cyclic group of order of F minus 1. So this gamma looks like this, it's an element of VFB. Now we study their conjugacy classes, and first of all this let's see this lemma, which plays a very important role in concluding the main result. It says that suppose we have a group which is extension of this some group K by H, where K is an abelian group, then for any element K in K, its centralizer in G is actually extension of K by its centralizer in H. So we use this lemma, apply this lemma for this group because it follows the same thing, and from here we conclude that since B is an element of VFB, we find the class length of B, which gives us the class length of any element of VFB actually. So now consider this set S. It consists of all the non-trivial elements of VFB into Z, where Z is any element of its centralizer in 1 plus gamma A. Okay, so this set actually partitions this VF D2PM minus 1 plus gamma A. Since this is a normal subgroup of VF D2PM, so whole group minus this normal subgroup is again a union of disjoint conjugacy classes, which are given by exactly these elements. Now come to the main result. It says that suppose we have any finite field of characteristic P, where P is an odd prime. If it has more than 3 elements, then D2PM doesn't have a normal complement in VF D2PM. And this is a brief sketch of proof. Suppose it has some normal complement, say N, then we can find a epimorphism from FG to G which fixes the elements of G, and it further induces, if this map is restricted to VFB, then all the it goes to this subgroup of G and thus maps the generator of this group to B only. And since you can check that this centralizer of B in 1 plus gamma A is actually contained in N, we can conclude that these many elements lie in this set, and since these elements lie, their whole conjugacy classes lie in this set, which actually gives us a contradiction because we know its order, its size, and these elements actually exceed the number from its size. So we reach at a contradiction using this information of classes over here. Now we try to conclude this problem for another class of groups, which is extension of a cyclic group of order 3 by any finite abelian P group. Obviously here we are taking 3 is dividing P minus 1. So suppose the cyclic group of order 3 is generated by some small b, and here again we have VFG as extension of VFB by 1 plus gamma A. Here we have this result regarding the conjugacy classes lying in VFG. It says that suppose we take some element in VFB whose centralizer in 1 plus gamma A matches with that of B. In that case, set of these elements form disjoint conjugacy classes in again this VFG minus 1 plus gamma A. So now the problem was to identify the elements in VFB which satisfy this, because in VFC2 it was quite obvious, but in case of VFC3 we know that any element looks like this, but we can't like directly say from here how is it connected to the centralizer of B in 1 plus gamma A. So because if both of one of alpha 1 and alpha 2 is 0, then it's quite obvious that this thing holds, but if both are non-zero, then we have V of this form. So we can say that centralizer of V in V is actually centralizer of B plus IB square in V, since these are only constants. But actually this lemma comes to a rescue, because it says that, note that here 3 divides P minus 1. So if we take this finite field of characteristic P, then it contains all the cube roots of unity. So excluding only those cube roots of unity, if I belongs to F minus I, then except for those, all the I in F satisfy this equality, that their centralizer V matches with that of B. So this helps us a lot to like get so many elements in this set, and these elements again help us to conclude this main result. It says that suppose we have a prime such that 3 divides P minus 1, G is A semi-direct product with B, where A is a finite abelian P group, B is the cyclic group of order 3, then for any finite field of characteristic P, G doesn't have a normal complement. We conclude this using the information of classes, but those help us only when the field is having more than 7 elements. For field with more than 7 elements, we prove it again by contradiction. Suppose we have a normal complement, then we can find a map from VFG to G with kernel N, and this map induces this 1 plus gamma A turns out to be extension of A with this subgroup, and finally using because we know that this set forms disjoint conjugacy classes in N minus 1 plus gamma A, we finally conclude that all these elements whose centralizer coincides with that of B, they actually give number of elements which is more than this set actually. So we again arrive at a contradiction. But the case for field with 7 elements, that we conclude with the help of symmetric elements lying in the semi-simple group algebra VFB. And for that, consider this lemma. Suppose we have a finite field of characteristic P where P is more than 3, then symmetric units form a cyclic subgroup of VFB with this order. And in particular, if we have 3 dividing P minus 1, then FB is actually direct sum of 3 copies of F, and so VFB is direct product of F star and F star. So one of these cyclic groups is given by actually the symmetric units in VFB. So using this fact, we were again able to find some elements in VFB which are in N, but they again give the contradiction to the size of 1 plus gamma A. this involves a bit calculations. Now, till now we have seen that if the group is not a P group, then most of the times the result is negative for the normal complement problem. So, here we prove the result for some classes of finite P groups, and it is affirmative in this case, and the class is actually of all the finite split meta-abelian P groups of exponent P, and we are taking the field with P elements. So, we prove that for these classes of groups the normal complement problem has a positive solution, and hence the isomorphism problem also. So, in order to prove this theorem, we actually make use of this lemma. It says that if we have an abelian normal subgroup of a finite P group G such that its commutator is contained in A and exponent of the group A is P, where P is an odd prime, then we have this isomorphism. We prove this actually making use of this map, which is from 1 plus gamma A to A. It takes any element x in 1 plus gamma A to this. A is mapped to the augmentation of its coefficient. Okay, so this map turns out to be an epimorphism with this normal subgroup of 1 plus gamma A as its kernel. So, this lemma actually helps us to prove the main theorem. Suppose since we are taking G to be a split meta-abelian group, so it is an extension of say B with say A, where A and B both are abelian groups of exponent P. In this case, we have this structure of VFG. So, now if we have the embedding of A into 1 plus gamma A, then we can see that 1 plus gamma A is turning out to be a split extension of A by this from this lemma. Similar way, VFB can also be written in this form using that lemma again. So, finally, we put this 1 plus gamma A in this form and VFB in this form, and we were ultimately able to prove that this turns out to be normal subgroup of VFG, which actually is a normal complement of G in VFG. So, this was the proof for some classes of P groups for which normal complement problem holds. Now, there are some questions which arise out of this work which can be addressed. First is that finite P groups of maximal class, nothing is known about them regarding this problem, because we do not know whether they are circle groups of some radical ring or not, because this result says if a group is of order P raised to n, then for it to be a circle group of some radical ring, the nilpotency class can be at most this. So, if the class is maximal, then nothing can be concluded from the known results in this direction. So, one can think about what is the solution to normal complement problem for these P groups of maximal class. Also, since we saw that for q equal to 2 and 3, we have concluded the normal complement problem, but for general or prime q such that q divides p minus 1, what can be said in this regard? That is also one of the interesting problems. Also, like we saw that Frank Roll connected the problem with the isomorphism problem, what can be said in that direction for groups which are not P groups actually? Maybe we can say order is divisible by 2 primes. In that case, nothing is known and there are no ideas how to start like this problem. So, these are some of the questions which arise out of this work. Then in the end, these are some of the references. Thank you.
In the cases where you can compute the size of the conjugacy class of a unit, can you say something about the centralizer in the unit group?
Actually, I am telling about the conjugacy class size only by finding what is the centralizer.
Okay, not just the order of the centralizer or
yes.
The structure of the centralizer.
Structure, yes, in the cases that I have discussed right now, it's turning out to be abelian actually. It was actually abelian. That helped a lot in like moving further.